So welcome to the first episode of Rockets and Coffee. I am here with Dr. James Lambert, and I'll let you explain your own background because I think I'd butcher it.
So my background is it's kind of diverse, really. I did physics and philosophy at university and stayed on to do a PhD in physics.
Yeah.
And then after that, I spent some time in education as a tutor and as a company founder. And during that time, I bumped into this chap called Richard Dinan, and we started penciling in interesting ideas to work on, and that gradually snowballed into Pulsar.
But what's your area of physics?
I suppose most of my work was in the theoretical end, so trying to connect physics up to computer science.
Okay.
And it's a weird, quite esoteric branch of theoretical physics that doesn't connect much to my day-to-day work at Pulsar at all. It was very sort of formal and mathematical,
Bit of a sidebar.
but fascinating. And I got roped into this topic in my fourth year as a student, and we had to do this group work project, and they give you a topic, and you have to go away and research it. And one of the topics was called the thermodynamics of computation. And
Okay.
I said, what on earth does that mean? That sounds like gibberish. And so I immediately signed up to that because that sounds fun. You know, I have a tendency of choosing projects that sound
Hard?
not just hard, but subjects where my immediate response is, I don't know what that means. That always kind of appeals to me. So I signed up for this course, and it turns out that a bunch of researchers at IBM had discovered that you could connect computer science to physics using the language of thermodynamics, like how much heat is stored in an object and how it processes thermal energy.
Oh, wow.
Which I thought sounded bizarre.
Yeah.
And the more I read about it, the more fascinating it became. And so that master's project turned into a PhD project. And then when I got to the end of it, I sort of figured I've spent enough time staring at this one topic. I need a fresh challenge.
Yeah.
So I didn't stay in research. Once I finished my PhD, I got out and went and did something else. So I worked in education for a bit. You know, a complete change from all of my work, because the work at university was very sort of esoteric and academic and obscure, and straight away I got into another job where it was all about explaining it to people in as clear a manner as possible, which was great. It was it was a refreshing change of pace.
Yeah.
Richard and I have known each other for about 12 years at this point. I lose track, but when we met, Richard had a long-standing conviction that he wanted to do a fusion project. He wanted to commercialize fusion technology.
Yeah.
And we spent several years batting around a few different ideas until everything came together in the form of Pulsar fusion.
Yeah.
And our insight was that if you want to do fusion, first of all, doing fusion in space is easier. And if you want to do space tech, well, what's the foothold? How do you get into this industry as a new scrappy startup challenger? And the idea was, well, we'll just get into the propulsion business because it overlaps on a technical level with fusion quite nicely. It's all about plasma physics. It's all about magnetic confinement. And it's a really nice way of just getting a toehold in a market. And also, if you want to build a fusion propulsion system for spacecraft, you should probably have some experience selling things and putting things on spacecraft.
So you mentioned that nuclear fusion is easier in space.
Yeah.
Do you want to
I can tell you
dive
about
into that a little bit deeper?
Absolutely, yeah. So take a conventional nuclear fusion experiment that you find around the world. Take a tokamak.
Yeah.
It's a big donut-shaped chamber, and you have to suck all the air out of it, and then you have to put a tiny amount of hydrogen in and heat it up.
Yeah.
Now,
To
if
the
you do this-
temperature of the sun, right?
Exactly.
Really, really
So
hot.
hundreds of millions of degrees. Now, if you want to do that on Earth, you have to suck all the air out because there's an atmosphere.
Yeah.
Straight away, if you're in space, there's no atmosphere.
It's no problem.
So if you look at the energy output of something like the ITER experiment that they're building in the south of France,
Yeah.
I think about 30% of its power output needs to just be funneled into their vacuum pumps.
Yeah.
You're just constantly running these pumps to prevent air getting into the experiment. Whereas if you're in space, straight away you can just use that energy. You can use it for propulsion, you can use it for running your instruments or whatever else you want.
What is it that you are most excited about achieving with nuclear fusion propulsion?
Well, I think the exciting thing about propulsion is that it's an enabling technology. You don't really know how it's going to get used until you build it. And people think, oh, actually, do you know what? Now I can design a mission to go to Neptune and orbit Neptune for 20 years and then fly back with all this data. So the exciting thing is we don't really know what the future of the space industry is, but we do know that the more propulsion you have, the more you can do.
Yeah.
You know, you can build space tugs that can pull entire space stations into orbit around Earth or transfer them to orbit around Mars.
Yeah.
You can send enormous scientific missions out to the outer solar system and back again. Or you can do things that no one's ever thought of yet because, you know, our imaginations are usually limited by what's immediately
What we
available.
know. Yeah.
Yeah, so it's hard to say, but it's exciting to always work on an enabling technology that you can put into other people's hands.
So how does it work in terms of propellants and the amount that you have to carry with traditional fuel? You have to have, you know, I know you said that nuclear fusion works in like a vacuum.
Yeah.
However, to then come back, is it a lot easier because they don't have to carry as much fuel to come back?
Yeah, what you've highlighted is like the fundamental difficulty of all space travel is that you have to carry your fuel.
Yeah.
And if you can switch to a more efficient propulsion system, which nuclear fusion propulsion would be extremely efficient,
Sure.
then you have to carry less fuel.
Yeah.
Which is wonderful. Your spacecraft is lighter. And there's this weird feedback thing where the more fuel you need to carry more fuel to boost that fuel that you need to carry. So it grows exponentially.
Sure.
But that goes in reverse. If you can reduce the amount of fuel you need to carry, the reductions also are exponential. You can massively reduce the weight of your spacecraft, the more efficient your propulsion system becomes.
Yeah, sure. So does that make it a lot easier for us to take, you know, humans into deep space?
Yeah, every kilogram of fuel that you're saving is a kilogram of people or instruments or whatever.
Yeah.
You know, or stuff that I haven't thought about yet, you know. It's all just more opportunity for us to explore the universe. Maybe it's interesting to just think about, you know, watch a movie like Interstellar and the big difference between the spacecraft that you see in those movies and the spacecraft that we would actually build in real life if you want to do that mission is that the spacecraft you build in real life would have enormous propellant tanks. It would be mainly a propellant tank.
Yeah.
You know, whereas in the movie, you just see this nice little capsule with a windscreen and people flying the spaceship. That's because they have to be using some kind of future propulsion system that's way more efficient.
Yeah, sure. Yeah?
So that's why the sci-fi movies always look really different to what you see when you look at actual space missions.
Okay, so speaking of TV then, because I think burning question, I'm a big Fallout fan, and in Fallout they do cold fusion. Is cold fusion a fringe tech? Is it a real tech?
No, it's not a real tech. So the term cold fusion comes from the 90s. There was this big scandal over some research that was published by some very, very eminent physicists saying we think we can do fusion, but at room temperature.
Sure.
And it turned out that they couldn't.
Yeah.
And I don't know whether the paper was ever retracted. I'm sure it was, but it turned out to be an absolute mess and not actually possible. So we retained the term cold fusion because it sounds really cool.
Yeah, it does.
But it's
cool.
But it's not a real tech, unfortunately. Yeah.
So cold fusion implies there's a hot fusion. What's the difference?
Oh, great. Yeah. All the fusion that we've been talking about is hot fusion.
Yeah.
Fusion only happens at very, very, very high temperatures for the reason that you're trying to fuse two hydrogen atoms or a hydrogen and a helium, and they really don't want to fuse.
Yeah.
So you have to get them up to incredible speeds so that when they collide, they have enough energy to actually join together and overcome their tendency to repel each other.
Yeah.
Hence hot fusion.
Yeah. So with hot fusion, how hot are we talking?
Yeah, really hot.
Really hot.
200 million degrees centigrade, something like that.
So when you're doing that in something like a tokamak, what on earth is holding that in? What material are we using that holds that kind of heat?
People think, if it's 200 million degrees, it must just melt a hole in everything, right? This is why you need magnets.
Yeah.
We actually take this very hot plasma and we just actually levitate it. We magnetically levitate it.
Yeah.
So it doesn't contact the walls of the reactor.
Which is why it has to be a donut, right?
Which is why it has to be a donut, yeah.
So does doing nuclear fusion propulsion work in a similar way? Is it also like a donut?
Not donut shaped.
Yeah.
Similar in the sense that you're still taking the raw fuel, hydrogen and sometimes helium.
Yeah.
You're still heating it up to a very high temperature, but you're doing it in a different shape. That's the main difference. Because if you want to optimize a system for propulsion, you need a way for things to be ejected out of the back of the spacecraft, right? So donuts very obviously don't allow this very well. You can vent things out of the bottom, but that's less interesting. So we look at linear devices rather than donut-shaped ones.
I see.
And linear devices, again, present a nice advantage in that you can use slightly weaker magnets for confining your plasma. You can use because of their geometry, you can have a smaller magnetic field. And again, you're spending less of your energy generating magnetic fields and more energy on whatever your spacecraft is there to do.
In the show, without spoiling it for you, they wear these big suits, kind of looks like the first Iron Man movie, like the very first Iron Man iteration looks very similar to that. Right. In the back of them, they have fusion cores in order to power them.
Cool.
If that was the case, would that not cause a certain amount of radiation that maybe would not be great for you? In the show, they also have rad away, which just gets rid of all the radiation, so they're fine.
Rad
but
away.
Yeah, in real life though, would I die?
Perhaps there's many different possible fusion reactions. Some of them produce neutron radiation, which is extremely harmful to people, and some of them do not.
Yeah.
So it depends what they're using.
Yeah.
The bigger problem is if it's small enough, making it small enough to fit in a backpack.
It's literally like this thing.
Yeah, that doesn't sound very doable to me. It actually comes back to this problem that plasma doesn't like to flow in a smooth manner. It tends to be quite turbulent. And usually the way we attempt to solve that problem is to make our reactors larger.
Yeah.
So miniaturizing fusion reactors is
So on that basis, because I'd love to hear a physicist answer this question, because I was asked it the other day, but nuclear in TV and in film glows.
Yes.
Is it green? Does it glow? Why do we represent it that way?
Is it green? Does it glow?
Yeah.
It does glow. I can tell you confidently, fusion plasmas glow.
Yeah.
They glow beautifully.
Yeah.
They are not green.
Yeah.
They are. It depends on the color of
the gas.
The gas, right?
Yeah.
So you're usually using hydrogen helium, so you tend to get a purpley glow. But as you know from fluorescent lights, neon lights, the gas you put in determines the color you get. So yeah, it glows.
So, but not
So
green.
actually, it could be green.
Could be
green. Yeah.
What would
neon's,
be?
I think neon's green, but I have to double
We have
check.
to fact check.
Yeah. You have to fact check me on that.
Oh, perfect. With nuclear fusion for propulsion, obviously there's been things thrown around about how it could take us to Mars in 12 days. And what is it that is so tricky to achieve that right now? What is it that you're researching specifically to achieve?
Okay, that's a really good question. Yeah, I think the hardest problem is that plasma physics is very hard. And if anyone watching it hasn't heard, like, what is plasma physics? What is plasma even? Imagine you take a gas and you heat it up so much that the electrons and the atoms are pulled apart.
Yeah.
This is what a plasma is. It's kind of this glowing, very hot gas that obeys very complex laws of physics. And although we know the laws of physics that it obeys, it's very difficult to actually model them on a computer. It's really frustratingly challenging. And so anticipating the behavior of a reactor is really hard.
Okay.
That's the main challenge we're trying to address. That's the thing that makes our work difficult. And so designing a reactor that is stable and efficient and doesn't melt itself to pieces at the temperatures is
Yeah.
hard. It's
Yeah.
really, really difficult.
Okay.
And without going into too many technical details, if you vary things like the pressure and density
Yeah.
of the plasma, you get very different behavior out of it.
Yeah.
So figuring out things like the exact temperature, pressure, and so forth allow you to dial in the correct design. But that's really difficult to do
Yeah.
because the computer simulations are not as accurate as we would like.
Yeah.
So those are the challenges. That's the main challenge we're facing.
So how do you even test something like that, right?
Yeah, you got to build it.
Yeah.
You've got to build it. You've got to build it. I mean, and computer simulations can tell you a huge amount. They can tell you that you hopefully in the right ballpark.
Yeah.
So something that people will come across if they do any research into nuclear fusion, after a while you come across this idea of instabilities.
Yeah.
Plasma really likes to be turbulent. It likes to sort of flip over on itself. It doesn't like to flow smoothly.
Yeah.
And so avoiding those instabilities is the number one challenge in all fusion research, whether it's for energy, whether it's for propulsion. It's avoiding instabilities is incredibly challenging.
Sure. So when you are testing something like that, is that something you test in space, or is that something you would test in, one of these huge vacuum chambers that we have behind us?
Both. I think first stage would be to test in a chamber on Earth, suck all the air out, ignite the plasma, and away you go. And then if that looks promising, we have plans to do an in-orbit demonstration as well.
So why is it that nuclear fusion propulsion creates so much, I guess, is it thrust, over conventional rocket propulsion?
Sure.
Taking us to Mars in 12 days rather than X amount of years.
The interesting the comparison between chemical propulsion like rockets and fusion propulsion is really interesting because they operate in very different regimes. So chemical rockets, like the kind that you see launching a SpaceX rocket into orbit, or chemical rockets you see in space, they provide very high thrust, but they do it in a very inefficient manner.
Yeah.
So they eject a huge amount of material into space in order to generate that thrust.
Yeah.
A fusion rocket, on the other hand, will produce a much smaller amount of thrust, but very efficiently.
Yeah.
It will eject its exhaust at an incredible speed, 10 to 100 times faster than a chemical rocket. So that's the trade-off that we're looking at going from chemical to nuclear fusion propulsion. It's that massive efficiency, which means your spacecraft does not have to carry very much propellant in order to achieve its mission. That's the fundamental value of a fusion rocket.
So there was something that I was talking to the Pulsar team about a while ago, just on a random Zoom call, and we were talking about propellants, and we were talking about like lunar fuels. Is that something that would be involved in a mission like that?
It could be, absolutely. The reason lunar mining the moon for fuel comes up is one of the most promising nuclear reactions for a fusion propulsion system is deuterium fusing with helium-3. Helium-3, type of helium, it's not common on Earth.
Yeah.
So you can either breed it in a nuclear reactor, but you can also find it on the surface of the moon.
Yeah.
So
as you do.
As you do. This isn't a plan you can put into progress next week.
Yeah.
But it's
maybe next month.
Exactly, next month. It's one of the concepts that's out there of where on Earth do you get helium-3.
Yeah.
And of course, it raises all kinds of fascinating engineering problems. How on Earth do you mine lunar dust, which is very abrasive and unpleasant? How do you extract helium-3 from it? Fascinating problem.
Yeah.
But yeah, that's one of the issues we have to look at.
Sure. So in terms of that mission, something else that you do at Pulsar is electric propulsion. So if you were to take a mission to Mars and you were to utilize nuclear fusion for that, would electric propulsion also play a part in, its certain area of orbit that's for?
Really interesting. It's hard to say. I think of nuclear propulsion is usually a much larger project, a much larger device than a Hall effect thruster.
Yeah.
So Hall effect thrusters, even the big ones that we make tap out at around 10 kilowatts. If you want to be fancy, you can even look at 20 kilowatts. They scale well, but a nuclear fusion propulsion system might be something like a megawatt.
Yeah.
So 1,000,000 watts, much more powerful. So they're really optimized for large scientific missions to the outer solar system, things that involve transporting people or lots of scientific machinery. Whereas Hall effect thrusters today, they tend to just go on satellites, a 1-ton satellite, 2-ton satellite, something like that, even down to quite small CubeSats.
Sure.
So it's hard to picture a nuclear fusion propulsion system being applied on a small scale.
Yeah.
It tends to only be big things.
Yeah. So with electric propulsion, I mean, give us an idea of what that's actually used for. I mean, I know it's used for satellites, but anything outside of satellites?
Sure, they're on the James Webb Space Telescope.
Okay.
It's a well-known science project, right?
Yeah.
And it's just sitting out there, hovering around in space, and these Hall effect thrusters are just there to maintain its position. So they call it, in the industry, they call that station keeping.
Yeah.
Super important, and it's just there to perform these tiny micro adjustments to keep it where they need it to be.
Yeah.
That was fun.
Nice.
That was fun. Thank you,
That was
Sophie.
fun.